So are you ready today?
Yeah.
Yeah, okay, great. So our next speaker is Tselil Schramm from Stanford, and she will tell us about graph matching in correlated random graphs via small subgraph statistics. Please, Tselil.
Okay. Thank you for the introduction. Thanks to all the organizers for the invitation. So I'll be telling you about graph matching in correlated random graphs with small subgraph statistics. And this is based on some joint work with Boaz Barak, Qining Xiao, Jishen Lei, and Yuki Shang. And I apologize to all of my co-authors for butchering their names. Um, okay, so here is the setting. So the problem that we're studying is the graph matching problem. And it's sort of like an approximate version of graph isomorphism. So my input is going to be two graphs on n vertices. And my goal is to find a permutation of the vertices that maximizes the number of shared edges. So if G0 is the first graph and G1 is the second graph, then and AG0 is the adjacency matrix of G0 and AG1 is the adjacency matrix of G1, I just want to permute the rows and columns of the adjacency matrix so that I'm maximizing their correlation. Okay, so for this G0 and G1, this permutation gets 4 shared edges. So the value of this permutation is 4. This permutation gets 5 shared edges, so the value is 5, and this is the maximum value. All right, so that's the goal. And please, like, stop me at any point if you have questions, or if I say something unclear. Okay, so our goal is going to be to design efficient algorithms for this problem. It's not so difficult to show if you're in the business of showing these things that getting a exact algorithm for this problem is NP hard. So we don't expect to be able to get this in polynomial time for worst case inputs. And we further have a hardness of approximation result based on something called Feige's random three-step hypothesis. So it's also unlikely, depending on what you believe, that we get a approximation algorithm for this problem on worst case inputs. Okay, so what we're going to do is today we're studying this problem in a randomized model. We're going to study the approximate graph isomorphism problem in GNP. And this problem was first suggested by Pedersani and Grossklasser, but it's been studied, in a number of follow-up works. So here I've only listed a couple of them, but just to say that this is like a well accepted average case model for this problem. So okay, so we'll consider the following planted model. Sorry, suddenly things aren't working so well. I don't understand. Let me start over. Okay, great. So we're gonna study the following planted model. So what we're going to do is we're going to sample correlated error-to random graphs. And the way that we do this is we first sample a graph from GNP, and we'll call this the base graph. Okay, and then we take 2 copies of G, and for each copy of G, for each edge independently, we subsample it with probability gamma. So with probability 1 minus gamma, we delete it. With probability gamma, we keep it. Okay, so these are 2 independent subsamples. Each of them has average degree p gamma n. So the marginal distribution of G0 and G1 is Gn p gamma. And now we'll choose a random permutation pi and apply it to G1. Okay, and then these are the 2 graphs that we see. And it's not so difficult to see that the value of this permutation is going to be something like p gamma squared and choose 2. That's just by reversing this permutation and then asking how many edges survive in both of the common graphs. Okay, then by simple concentration arguments, you won't get any permutations gets a better value for the graph matching problem. And just in order to kind of fix a setting of parameters in our minds, like the interesting set of parameters for this talk are going to be, you should think of gamma as being like a small constant, like 1 over 100, and you should think of p as being like 1 over n to the 0.999. So we have graphs, and their average density or their average degree is polynomial in n, but a small polynomial in n. Okay. And for the purpose of comparison, I want to bring forth the following null model. So in this model, what I'm going to get is I'm going to get two graphs, and I'm going to sample each of them independently from G and P gamma. So that's like the marginal distribution of each of these graphs, but I'm going to take two completely independent samples. Okay, and here, it's also not so hard to see that the maximum value of the graph matching problem is going to be P squared gamma squared and choose 2, right? So if I just take an arbitrary permutation, this is going to be the probability that the edges are present in both graphs. And again, in this regime of parameters, the concentration is strong enough that basically you'll get the same as the expectation up to lower order terms. Okay, so the question that we want to ask is, when can we recover the maximizing permutation pi? When can we know what the best graph matching is? The following theorem of Kulina and Kibayash establishes that you can only recover the permutation pi when you have that P gamma squared is bigger than log n over n. And this corresponds to the setting where if you look at the sort of intersection graph, so you think about the case when pi is the identity and looking at which edges are present in both graphs, this is exactly when this graph is connected. Okay, this is the connectivity threshold for that graph. It makes sense that below the connectivity threshold, there would be more than one permutation because you'll have isolated vertices that could be mapped to each other. So okay, but when you are above this threshold, then you can do recovery. Okay, so our goal will be to do recovery when this condition is met. All right, so how should we efficiently recover the permutation? So for the average case graph isomorphism problem, there are algorithms that succeed. Okay, so one such algorithm is to match local neighborhood of vertices. But the issue is that in this situation where your graphs are only correlated, they're not identical, such algorithms will fail. And I'll try to convince you why for maybe 2 slides now. So what you could hope to do this to do the same sort of thing, right? Like you could hope to take vertices and then match some radius k neighborhoods. But because we're applying such high level of noise, the correlation between these neighborhoods won't really be so high, right? So the local neighborhoods of the vertices really change. I mean, you can think of having like an identical, like G n P gamma squared, and then adding P times enough edges to get P gamma to each of the copies. So then you can see that the local neighborhoods won't look so similar in the 2 copies anymore. So this type of algorithm doesn't seem like it's going to work. Another algorithm that works well for average case graph isomorphism is you take the adjacency matrix and then you compute the top eigenvector, and then you order the vertices according to the entry value in the eigenvector. Right. Okay. So, but that also is not going to succeed for similar reasons, because when we do the subsampling, this is like adding a random matrix whose norm has is like 1 minus gamma the norm in Frobenius norm to the current matrix, right? So in what's going to happen is that the top eigenvector is going to get totally messed up, and it's not so difficult to convince yourself using a small calculation that once you add this noise, the top eigenvectors of these graphs are only going to be like polynomially and gamma correlated. Okay, so this strategy of looking at eigenvectors and ordering the entries, it's no longer going to just work. Okay, so we're not going to do that. So what have people done to solve this problem? So before our algorithm, all the prior work essentially had the following idea. So you assume that you have some start information, or what's called a seed, right? So you assume that there's some set S and in G0 such that you know the permutation of S into G1. Okay, and then once you have this, and like if you think about applications of this problem, many times the application are you have 2 networks, like 2 social networks like Twitter and Facebook, And some people, like, obviously, which people in Twitter map to which people in Facebook because, based on their names. Some people have handles that you don't know, so you can sort of start with this like initial seed information and then like bootstrap from there. So in some settings, this makes sense. You have some domain knowledge, and then you can do stuff like if you have a seed that's polynomially large, like size n to the epsilon, where this epsilon should depend on your average degree, you can just do a really simple percolation to recover the permutation. So that's due to Yartseva and Grossglasser from 2013. And then sort of concurrently with our own paper, another paper came out by Elchanan Moser and Jiaming Xu, in which they show that you can achieve the information theoretic limit, but you still need a seed which is polynomially large for most values of p. Okay, so there's some complicated relationship between the value of p and the size of the seed. For almost every value of p, you would need still a polynomial size seed. And if you're in our setting where we assume that you don't have any domain knowledge, you don't start with a seed, then all you can do for these algorithms is you can sort of guess a seed, right? So that requires choosing some subset of vertices here and then guessing which set that they map to here, and that should take exponential in the size of the seed time. So prior to our work, all that was known was sub-exponential time algorithms for most values of p. Okay, so our result is that for p in a large range, which I want you to not think about too hard for now, I'll show you like a little picture later, and for gamma bounded below by a constant, there's a quasi-polynomial time algorithm for recovering pi with high probability. Okay, so we get down from sub-exponential time to quasi-polynomial time, so we're almost efficient. Okay, so yeah, what's up with this weird range of degrees that we handle? This doesn't look so good. I agree that it's a little bit embarrassing. Yeah, we can handle GNP with average degrees that are, kind of smallish, but n to the little o1 to n to the 1 over 153. This constant wasn't optimized necessarily, or average degree bigger than 2/3. And it's actually even weirder. We can also handle a couple of discrete points in the middle. Okay, so yeah, so this is not a book proof. I guess I'll say, but like later, I hope it will become clear why this happens. And I actually think that our techniques should work all the way through this range. Anyway, okay, so this is like a little mystery that we'll resolve later. And for those of you who are interested at home, we can actually handle noise rates that are, or yeah, subsampling rates that are slightly subconstant, right? So if you want like 1 over log n, then we can handle that. And if you want, 1 over q, I guess, then the q will show up in this exponent. So anyway, that's that for the main result. Here's a little, so our main result is quasi-polynomial time. But if you care also about the hypothesis testing problem, where you try to distinguish this planted model from the null model that I mentioned before of just two completely uncorrelated random graphs, this we can do in polynomial time. So for p and gamma, basically as above, we can get a polynomial time hypothesis testing algorithm that tests between the planted and null distributions.
May I ask, I'm just worried about the word pseudo. What's pseudo?
Yeah. Okay. So pseudo means that it's polynomial, but it's polynomial in the
not a bit
numerics of the.
Not a bit, but okay. So got it. Okay.
Yeah, pseudo polynomial time.
Mm-hmm.
So meaning that like it's polynomial, but also in the length of the integers that describe the problem, right? So okay, what's really going on here is that if p has like really large bit complexity to write down, then our algorithm takes more time, and it will be clear why a little later, I hope.
Thanks.
All right. Okay, so that's the result. I am yeah, I guess like if there are more questions now, you should ask, but it doesn't seem like people have questions, so I'll move on. So okay, so our approach is going to be to count small subgraph statistics. For hypothesis testing, what we're going to do is we're going to look at the small subgraph counts in each of the graphs, and we're going to see how correlated these are. And for recovery, we're going to do something which is matching rare subgraphs. Okay, so this is just you know, if you don't want to know anything about the proof, and all you want to remember is vaguely what we did, this is it. But now I'm going to, for the rest of the time, explain to you how the small subgraph counts work, and some interesting concentration questions will come up. Okay, so I'll start by telling you about the hypothesis testing problem, because it's simple and it illustrates the main ideas of our approach, and then later I'll tell you about recovery. Okay, so hypothesis testing. Okay, so we're given two graphs. They're sampled equally likely from the planted distribution or the null distribution, and we want with high probability to be able to tell which distribution they came from. That's the problem we want to solve. Okay, if we didn't care about computational efficiency, then there's already an algorithm that we can use, right? There's a brute force algorithm which we can use. A good test that tells these apart is what is the maximum value of the, or what's the best matching between the two graphs, right? So if there's a permutation that gets at least p gamma squared n squared matched edges, then we know that we're in the planted distribution. Otherwise, we're in the null distribution where the value was p squared gamma squared n squared. Great. Okay, but we want to do this efficiently. So you know, there's not so many things that you can do efficiently with graphs, right? But one thing you can do is you can count small subgraphs. Okay, so let's try to see what happens when we count small subgraphs, and let's start with the nicest subgraph, arguably the triangle. So I'm going to define this polynomial, core K3 of G0, G1. And what this is going to be, it's going to be the product of the number of triangles in G0 times the number of triangles in G1. Okay, so if I'm in the null model, the triangle counts are independent. And there's going to be something like, you know, like n choose 3 times p cubed times gamma cubed triangles per in G0, and the same thing in G1. So the value of this polynomial is going to be something like p gamma n to the 6 in expectation. I'm you know, like I'm going to be very loose with the constants here because it won't matter. So okay, so that's the value in the null case. In the planted case, the triangle counts are a little bit correlated, right? So because if I have a triangle appearing here, and I look at the reversal of the permutation from G0 to G1, it's more likely that the triangle will appear there as well. So this value is going to be something like the same, you know, p gamma n to the 6 for uncorrelated pairs of triangles. But then for the n cubed correlated pairs of triangles, I'm going to get only p gamma squared n cubed. Does this make sense? Right, so for the n choose 3 triangles that correspond to the identity permutation, there's going to be probability p cubed that they showed up in the base graph in here, and then times gamma squared cubed that they survive into both copies. So, okay, so things are looking great. It looks like I've got a pretty nice estimator, right? Like the expected value under the planted distribution, oops. Sorry, I am apparently not great at this. So, okay, so the expected value in the planted distribution is bigger by a little bit than in the null distribution. But now what we want to do is we want to understand if we also get concentration. Okay, and we can see that there's kind of a problem here, right? So like even if we're optimistic, and I'm going to return to this optimism later. So suppose that we're as optimistic as possible, then we would have that the variance or the standard deviation of this quantity should be something like the square root of the expectation, right? But then if you compare these two numbers, here you can see that the standard deviation is off by a factor of So this is larger by a factor of gamma cubed. Okay, so the estimator is okay for the expectation, but it has bad variance. All right, so what are we going to do? So, I mean, if I could have, let's say, capital T independent trials of this experiment, then I would be able to drop the variance. So imagine that you get, instead of getting just one copy of G0 and G1, imagine that you get, T independent experiments, right? So then the expectation won't change in the planted case. The expectation won't change in the null case either, but we'll be able to reduce our variance by something like 1 over square root T, right? Just using kind of these standard calculation arguments. And now we can see that if we can take T to be at least 1 over gamma to the 6, then the variance or the standard deviation will be smaller than the expectation, and then we'll have a good hypothesis test. Okay, you have to bound the variance in the planted case as well. All right, so I mean, this is really silly because the problem specification is that you get one copy of each graph, so that's not going to work. So instead of independent trials, we're going to try to find subgraph counts that are nearly independent. Okay, so suppose that we have T different subgraphs. Let's say that you can think of H1 as being triangles, and HT is like some other crazy graph. If we have T independent subgraphs, then we could do this same experiment. We could have the correlation be the average over these T different subgraphs of the correlation of those subgraphs. Okay, and now the question is, what properties do these different subgraphs have to be in order to have independent seeming subgraph counts? Okay, so now we return also to the question of concentration in general, right? So this is something that like I think Erdős and Rainey in their first couple of papers about Erdős-Rainey graphs already realized, but subgraph counts concentration in GNP is a little bit more delicate than you might initially realize. So to illustrate this, let's look at the following example. So suppose that I'm in GNP and I'm in the setting where P is like n to the minus 6/8. I know that I can reduce this fraction a little bit, but in a moment you'll be grateful that this is what it's like. Okay, and say that I want to know the number of copies of this graph H. It's like a K4 with a tail of length 2. Okay, so how many labeled copies of H exist in G? So if you compute the expectation, this is just going to be something like you take the n choose 6 possible vertices that H could be on. Oh yeah, this has 6 vertices and 8 edges, right? So you take you choose vertices that H could be on. You take the number of distinct labelings that you could take for those vertices, right? And then you take p to the 8th. That's the probability that all the edges are present. So that's like order 1 for this setting of P. Okay, so I expect to see constantly many H and G. But now if we zoom in on this K4 that's a part of H, how many labeled copies of this will we see? Well, we can do a similar sort of computation. There's going to be n choose 4 vertices and there's 6 edges. So p to the 6 is the probability that we'll see one. And for this setting of P, this is subconstant. It's like 1 over root n, right? So what this means is that, and now you can you can apply whatever Markov's inequality and see that in a typical draw of such a graph of such a GNP, you don't expect to see any K4s at all. And so what this means is that the count of H in G does not concentrate at all around its expectation, right? There's some low probability event, the presence of a K4, which means that once there is a K4, there will be many, many copies of H, and that's what drives the variance. Okay, and yeah, and now once you know about this, it's kind of an exercise to see that if you have a constant size graph, the variance in the number of copies of H in your graph is going to be like proportional to the expectation squared divided by the expectation of the minimum, it's divided by the expectation of the subgraph of H with the fewest expected number of appearances. So, okay, and the same thing, it doesn't only compute, or sorry, it doesn't only control variance, it also controls covariance of different subgraph counts, right? Because you can imagine that the same sort of thing will happen for this graph H and this graph H prime, you know, because they're different subgraph counts, they both contain a K4, you know, so this means that the covariance will be very different from the so you know, once there is such a K4, then there will be many copies of H and H prime co-occurring. All right, hopefully this is clear. People look a little bit confused on the Zoom.
I think it's clear.
Okay. All right, so the property that we're going to want our subgraphs to have is called strict balance. So again, this is a property that was already identified by Erdős and Rainey in their early studies of subgraph counts. But okay, so we say that a graph is strictly balanced if all of its strict subgraphs have smaller edge density. Right, so subgraphs that are strictly balanced include cycles, trees. Subgraphs that are not strictly balanced include, you know, our friend H from a couple slides back. You know, this cycle with a hair dangling off it, if you remove the hair, you're going to get a denser subgraph. Two copies of the same graph, you know, if you take one of them, you'll get a graph of the exact same density. All right, but if you have strict balance, then, and also you have it set up so that the expected number of appearances is constant, then any strict subgraph has super constant expectation, right? Because the ratio of vertices to edges will be larger. And for this reason, we'll have that the variance, based on the calculation on the previous page, the variance is going to be little o1 of the expectation squared. And so now, by, you know, second moment method, we get concentration of the subgraph counts around the expectation. And not only will we get concentration of the counts, but we'll also get near independence. So asymptotically, the counts will be independent. So the counts will concentrate around the means. And also, for any pair of distinct graphs, I and J, or HI and HJ, the expected product of the counts is going to be like basically the product of the expected counts. Okay, so that's essentially what we wanted. So now we have our testing algorithm. Our testing algorithm will be, we'll choose some set of strictly balanced graphs with some number of vertices and some number of edges chosen so that the expected number of appearances is constant. Because this is the regime in which the sort of concentration arguments from the previous slide will kick in. Okay, now we're going to compute the average correlation of the subgraph counts in the two graphs. Okay, and then we'll apply some threshold. And if this value is bigger than the threshold, then we'll say that we're in the planted case, and otherwise we'll say we're in the null case. So that's our hypothesis test. Okay, and the analysis is essentially what I described to you in the previous pages. You know, the expectation in the planted case will be larger by you know, n choose v times, you know, gamma squared p to the e factor. And the variance in the null case is going to be like the, you know, like a square root of the expectation, and we get to divide by 1 over root t. So as long as we take t to be inverse polynomial in gamma to the e, we get that the variance in the null case is small compared to the increase in expectation in the planted case. Okay, so now we're going to require that v. So now the question is, how big should we take v and e, right? Like our algorithm is going to be to count all subgraphs of size, or some number of subgraphs of size v. So basically, so our algorithm will take time, something like n choose v times t. Right. Now I'm doing the runtime analysis. And okay, and because there's only v squared choose e graphs on v vertices and e edges, and we need this to be bigger than t, needing this to be 1 over gamma to the 2e, we can conclude that v has to be 1 over polygamma. So that's what's going to govern our runtime. Okay. So as long as gamma is a constant, then our algorithm runs in polynomial time. So that's essentially it for the analysis of the testing algorithm. What I didn't do is I didn't analyze the variance in the planted case. But this is just, like once you have the strict balance property, then things concentrate around their expectations and things work out. Okay, so the one thing that we didn't do, so I told you that we have this hypothesis testing algorithm, assuming we have a sufficiently large set of strictly balanced graphs. Okay, but now what we need to get a set of sufficiently large or sufficiently many strictly balanced graphs. Right, so I added a bonus section where I tell you about what these test graphs are. Okay, so we need to argue that the test set exists. We want to take v to be 1 over polynomial and gamma, and then we want to choose v to the e strictly balanced graphs, and we need to set v and e so that the expected number of appearances is constant. So this is all very overwhelming, but you remember this weird thing that I showed you at the beginning of the talk where I said that we can only handle certain degree regimes for GNP. Okay, so this is the reason why. So the fact that I need to set the expected number of copies to be approximately 1 for concentration reasons will tell me what the ratio of vertices to edges that I get is. So this fixes, oops, sorry. So this fixes v over e, the density. Right, and then we need to find sufficiently, so what I want is I want that for any density, I can find a sufficiently large number of strictly balanced graphs at that density. And we can only do it at these densities. So in all the other regimes, we don't know enough strictly balanced graphs. Okay. So hopefully that made sense. Okay, Boaz, were you going to ask something or?
No, I just need to think, but nothing to ask. Okay.
Okay, so first of all, let's like ask ourselves, where will we find strictly balanced graphs? So here is a claim that's going to be very easy to verify. So the claim is that a connected deregular graph is strictly balanced. Okay, and the argument is, if you take any strict subgraph, the average degree will be strictly less than d. Okay, so awesome. So that's really good. So now what we're going to do is, if you have a ratio e over v, which corresponds to an integer average degree, then we can just take, a random deregular graph. Okay, so how many deregular graphs are there? There's if the number of deregular graphs on v vertices is v to the omega of d v. Okay, and so we're clearly satisfying this requirement. If we just pick a random deregular graph, we're going to be fine. Okay, so that's good. So anytime when this quantity is an integer, we're good. So we filled in all of these like discrete points along the spectrum. Okay, what about non-integer average degrees, right? So we still need to handle like many E over V which don't correspond to integer degree. So okay, so when 2 times E over V is a convex combination of two integers, d and d plus 1, what we do is the following. We sample a deregular random graph on V vertices, and then we add a random matching on lambda V of the vertices. Okay, so we'll get a graph with a correct average degree. And now the question is, will we still have the strict balancedness property? But okay, so the original deregular graph was strictly balanced, and now we just need to argue that when we added these extra vertices or these extra edges, we didn't mess up the strict balance property too much, and things here end up being fine because of expansion. So if you add a random matching to a deregular graph, you're not going to mess things up too badly as long as the matching is random. I mean, if I added it all to like one tiny set of vertices, like if all of the edges were that I added were in here, then I would be in trouble, right? Because this would be like a very dense subgraph, but this doesn't happen because of expansion. Okay, so when we do this, we fill in this regime of densities, which correspond to average degree bigger than 3. Okay, but what if the degree is less than 3, right? So the problem is that we can't do this because two regular graphs don't expand, right? Like random two regular graphs don't expand. Okay, so what are we gonna do? Here I realize that this looks like a heart, and it's but I really mean to say less than 3, even though I also love non-integer degrees. So okay, so what if we want this? So what we're going to do in this case is we'll do something else. We'll start with a 3 regular random graph on lambda v vertices. Okay, and then we take each edge and we'll subdivide it into k or a k plus 1 length path randomly. By choosing k appropriately, we'll get this to be the typical average degree. Okay, we have to choose the correct combination of k and k plus 1. And now we'll still have strict balance, again because of expansion, but we're only able to argue that we have the necessary strict balance properties when the ratio between k and k plus 1 is not so large, right? So this is probably it might be a shortcoming in our analysis. I'm not totally sure. There also could be other constructions for strictly balanced graphs in this regime. Okay, but as the difference between the k and k plus 1 path gets smaller and smaller when k is large, this becomes easier and easier to argue, and this is kind of the regime where we can do it.
So may I ask, my intuition is actually the opposite. So I missed something. I would say that if you just subdivide in 2 or 3, then you keep the strict balance. But if you have long chains, then you can get.
So imagine that by accident on like one, like in one chunk of the graph, I didn't subdivide any of the edges. Like imagine that the k, like we're looking at k equals 1 and k plus 1 is equal to 2. Okay, so that's like what's kind of happening like right here. So in that case, like if I accidentally don't subdivide any of the edges in some part of the graph, then that is really dense compared to the part where I did subdivide the edges. So you just want the difference between like the number of, yeah, exactly. Okay.
Thank you.
Yeah, sorry, I'll just finish the sentence. You just want the difference between having subdivided into k and having subdivided into k plus 1 to be like negligible, and that happens as k goes to infinity. Okay, and we're able to get it for the k that corresponds to n to the 1 over 153. Probably like maybe if we worked harder we could get that to go up further, and like I actually sort of conjecture that this kind of construction should work in this whole range. But we didn't. I mean, we didn't prove that for this result. Okay, yeah. So like I would conjecture that our construction would demonstrate test sets for all, like densities that you would need. Also, it's possible that you could do things like look at like labeled graphs in order to, get like a different version of strict balance. So anyway, I mean, I think there's all kinds of ways that one could imagine filling in this regime with similar ideas for what you're like subgraph counting, the overall strategy of subgraph counting and applying a threshold. Okay, so one more thing is that, so here things were really nice because we were working in the regime where V, the number of vertices, remember this was like 1 over, gamma to the whatever to the 10 or something. And gamma was constant, so these are constant size subgraphs, right? But for recovery, as I'll explain in a moment, we actually have to work with logarithmic size subgraphs, and then like everything gets really annoying. Like strict balance is no longer enough. You need some kind of stronger version of strict balance, which says that every subgraph that contains like a 0.9 fraction of the vertices has density strictly less than the quantity that's more than like less than 0.9 times the density of the whole thing. Okay, and that I mean that's something that we have to handle. So not only do we need to have strict balance, but we need some like quantitative version of strict balance for the recovery. And because all of the graphs that we're working with are really nice, like random graphs or like simple perturbations of random graphs, it's not so hard to establish this. But okay, I mean that's just to say that we like there's a little bit more work also that needs to go into it. Okay, so now I guess I'll tell you about recovery kind of briefly. Okay, so the first thing that I want to convince you is that distinguishing is actually not enough in order to get recovery. So just because we can tell that the graph isn't just like two completely uncorrelated copies of GNP, that doesn't mean that we're going to be able to recover the permutation very well. So like once you distinguish, there's some ambiguity in the matching. Like how should you conclude that two vertices be mapped to each other? One thing that I want to point out is that in our distinguishing algorithms, our subgraph had constant size. Okay, and we set things up because we wanted our concentration arguments to be easy, so that every copy appeared a constant number of times. So actually, like only a constant number of the vertices in the graph are even going to be like touched at all by anything we saw in our distinguishing algorithm, and for recovery, we need to work much harder. Okay, so here I'm going to say something that's, I mean, okay, so this is like a little bit of a cartoon version of what we do for recovery, but it definitely captures the main ideas. So what we're going to do is we're going to identify rare subgraphs that appear in both graphs. The rare subgraph here represented by these little squans. And we're going to match the vertices in the rare subgraphs. So we're going to choose, again, a set so that the expected number of the graphs that survive subsampling in both copies, right? So this is like, like there's like n choose v of them. And then in order to survive subsampling in both copies, again, like every edge has to survive with, or has to exist in the original graph and then survive into both graphs. So that's probability gamma squared to the e. So we want this to be much larger than the expected number of unrelated pairs, right? So for an unrelated pair, you can choose n choose v of them in the first graph and n choose v in the second graph, and then p gamma to 2e. Okay, so we just want to have graphs that are more likely to have appeared in the base graph and then survived independently into the two copies than to appear independently in both copies. Okay, and now if we see such a rare subgraph in both copies, it's more likely that it's because the vertices should actually be mapped to each other than otherwise. And what we can do is we can just like match the vertices in those two copies and be pretty confident that we're done with that there. Okay, but now if you sort of simplify this, it's like like couple seconds of algebra that I don't want to do, you see that this is actually corresponding to the condition that the expected number of copies is less than 1 in the original graph. Okay, and we still want it that to be the case that every vertex appears in such a graph. Otherwise, or like at least a polynomial fraction of the vertices appear in such a graph. Otherwise, we won't be able to match more than constantly many vertices. So, and remember that there's like if there's v vertices and e edges, then optimistically there's going to be like, v squared choose e such graphs, and this is like v to the e, and we need v to the e times the probability of a single graph appearing, like n to the v p to the e. This is we need this to be bigger than omega n if we want every vertex to appear in a copy of a rare subgraph. Okay, but because this is less than 1, what we're really asking is that v to the e be bigger than n, and that means that we need to take v to be growing with n, right? So we take v to be logarithmic. Maybe we could get away with log n over log n. Okay, so right. So if we choose v so that there's logarithmically many vertices in each, then we can guarantee that like a constant fraction of the vertices in the graph participate in these things, and then we can use similar percolation type of ideas. Like this will be our seed essentially, and now we can use the seeded matching algorithms that exist before in order to get the full matching. So we recover pi completely. Okay, so okay, so here are like claims that are just like not really true, but imagine they were true, and then the analysis would be correct. And then if you want to really know the analysis, it's like a slightly more complicated version of this. But the claim would be, there would be at the most one copy of each rare subgraph in the original graph G, the base graph with high probability. Okay, and the second claim would be that a constant fraction of the vertices in the graph appear in a rare subgraph in both copies. Okay, and once we can establish these things, we're done. And okay, and then we establish robust versions of these claims using like a more complicated version of the analysis that we did for the hypothesis testing, and then that gives us the algorithm for recovery. Okay, all of our proofs use the second moment method, and we're in this challenging regime where the expected number of subgraphs is less than 1. It's like 1 over it's quasi polynomially small, so that makes things like pretty tough, but we do it. Okay, so I have some remarks in conclusion that are a little bit like they're very zoomed out. So I don't know if how people feel about taking like a more speculative couple of minutes. How much time do I have? I have 7 more minutes, or?
Yeah, including questions. Yeah. Mm-hmm.
Okay, 7 more minutes including questions. Okay, so. Okay, I'll just do it, and
just do it. Yeah.
Okay, yeah, I'll just do it. Okay, so let's zoom out a little bit, right? So okay, so what I've shown you so far, I showed you a natural version of graph isomorphism. I showed you an algorithm that can recover the isomorphism in average or in correlated random graphs. There were some non-trivial concentration concerns that came up along the way, and we managed to solve them in a large regime of the information theoretically interesting parameter range. But I mean you can also see this as part of a like as a question that's situated in a larger sort of body of work, where we want to understand information computation trade-offs in estimation, right? So okay, so the problem that we considered was an estimation problem, right? So we had some prior on matchings and pairs of graphs, and our goal was to estimate the matching seeing only the 2 graphs. Okay, so we wanted some function of the graphs that would give us the matching. All right, and our measure of information was the correlation between the 2 graphs. So this correlation gamma. And the one complexity measure that you could take, so running time is a natural measure of complexity, but you can also see the measure of complexity as the degree of this function f that we're looking at. So this is like the measure of complexity that I'm proposing that we use, it's pretty, like in classical complexity theory, many times people are looking at the degree of the polynomial to compute something as a measure of the complexity. So that's going to be our proxy for the computational complexity. Okay, right. So and one reason why a degree is also interesting for estimation tasks is that like if you are looking for an estimator that's going to be robust to noise, then many times a high degree estimator is kind of not going to be very effective anyway, because high degree functions aren't robust to noise. So here, like if we want our algorithm to work just as well if the graphs are gamma correlated or like gamma minus epsilon correlated. So degree is a natural thing to consider here. And the question in general that we're trying to ask is, for which information rates is polynomial time estimation possible? Okay, or for which information rates can we design low degree estimators? So if we're looking at this hypothesis testing question, right, then in hypothesis testing, rather than estimating something, we want to distinguish structure from just pure noise. So like just distinguish this like structured Planta distribution from our null distribution. And here, there's some sense in which the optimal one-sided hypothesis test of a fixed degree has a closed form. Okay, so what does it mean to have an optimal one-sided hypothesis test? If you only care about one-sided hypothesis testing, you can just always output like, null no matter what. But here I mean optimal in that it's the solution to some relaxation, to some convex relaxation over the space of polynomials that tries to solve for a hypothesis test with bounded error only in the null case. Okay, so it turns out that the optimal such test of degree D has a closed form, and in some work of Hopkins and Stoyer, building on a result of Barak, Hopkins, Kellner, Qatari, Moiter, and Patachin, they propose the failure of the one-sided hypothesis test as evidence for hardness of estimation. So this is like a lower bound against low degree polynomials is evidence of computational difficulty for the estimation task. And they also show that this degree D hypothesis test, even though it only has one-sided error bounded, it can be modified to also give estimation algorithms. So you so like when the hypothesis test is bad, it's bad. Like you cannot do estimation. When it's good, then there's always an algorithm is kind of the claim. And this is like a very appealing sort of point of view. And it's been successful not only in community detection, but in several other problems as well. So it's a more general framework. And this work gives a constant degree hypothesis test algorithm and a logarithmic degree estimation algorithm for graph matching. Within this framework, like it's not so difficult to convince yourself that when you're counting small subgraphs in GNP, this is basically like a bounded degree algorithm. The degree is like the size of the subgraph. So the thing is that you can look at this work as sort of a stress test to this framework that Hopkins and Stoyer propose. So one thing that happens is that permutations or matchings are more complicated than just labelings, like labeling each vertex to be like in one of two communities, right? So this is why we get like a logarithmic blow up here, and we only get quasi-polynomial time algorithms rather than polynomial time algorithms. Another thing is that actually, like our hypothesis test is not this supposedly optimal one-sided hypothesis test because of the non-concentration of small subgraph counts, right? So because of this issue of strict balance, we actually have to modify this hypothesis test a lot in order to get an algorithm that works. So, okay, and then, yeah, great. So this is just to say that because the variance of the structured prior is difficult to control, two-sided hypothesis testing is different than one-sided hypothesis testing. Okay, so yeah, so that's just all I wanted to say. Like, you can also contextualize this work in this study of whether whether low degree estimators are a good proxy for computational complexity of estimation in general. And the answer is, based on this paper, it might still be the case that it's a good framework for understanding, but things aren't as simple as they would otherwise appear, as posed in this general framework. All right, well, I can sort of see that, you know, people look a little bit lost. Maybe that didn't make sense. That's okay. Going back to some more concrete questions to conclude. So I think pretty clearly the big open question is, can we do recovery of the permutation in polynomial time? So, you know, like, many variations on our theme are possible, or you could try something completely different, like using convex relaxation. So convex relaxation are known to work when the noise rate is very small. So when you have like 1 minus little o1 correlation, is it the case that convex relaxations could succeed for gamma like 1/100? Another possibility is that you really require quasi-polynomial time for this approximate graph isomorphism in random graphs. And I guess seeing lower bounds for that would be pretty exciting. So can you prove lower bounds, for example, in this low degree estimation framework for this problem? Okay, another question is, can you achieve the information theoretic threshold? I think, okay, so in the previous Simon's workshop, Jiaming Xu gave a talk, and he alluded to the fact that they have a result for this hypothesis testing question in all of the parameter regime, but I think it's not public yet. So looking forward to hearing more about that. Okay, and then the last thing is, can you take our subgraph counting approach and come up with practical heuristics that are based on this approach that will work not only in average case instances, but in other graphs as well? I think that's a really nice direction for future research. Okay, thanks.
Thank you very much, Lil. Any questions? I have a question, actually, even two questions. The first question is about this recovery in polynomial time. I mean, no, not really polynomial. So you had your algorithm works in n to the log n. Now, suppose you want to improve it to n to the power epsilon log n. Just one thing, I noticed you construct a seed which is really large, omega n, right? And
Yeah.
you quoted some result that says it's enough to construct a seed of omega of n to the epsilon.
Yeah.
So why wouldn't you just take a smaller seed and apply that result and save some running time?
Right. That may very well be possible. I guess that there's this other. Okay. There are a lot of you know, moving parts. One thing is that you need to have sufficiently many subgraphs as well in order to make the concentration argument go through, right? So it's so even now it's not like we get like n to the order log n, but you know, here I think like there's like a pretty large factor sitting out front, and maybe we could drop it down to you know, like 1,000 divided by, you know, something if we only went for epsilon. Yeah, but I think that like log n over log n is also maybe possible. So I think if you push our current strategy to its limits, I think maybe you could get log n over log n. Yeah.
Okay, I see. And my second question is more how would you call it, zooming out question. So if I think about it from the point of view of old-fashioned, I mean, signal versus noise. So the noise is GNP, right? Just on, but somehow the planted thing, I'm not sure I would get for the signal another GNP. Maybe so. And also, I think that from your proof, you don't for the planted case. Could you get away with something which is not just GNP? So the best thing would be arbitrary thing of just with some density, or maybe density and expansion. So that's just a more general question.
You're asking if there's a different model that makes sense for the structured case?
So especially for the planted piece, that will not be just random, something more general. That's it.
Well, okay, so I mean, our method is really, we're really using that we know something about the subgraph counts, and I guess that, yeah, like so for, I think for our style of methods to work, then you'd need a planted model where this
Expansion.
approach could make sense. But it's, I mean, like in general, there's no reason why you should only consider the correlated random graphs model for the planted case. And I think, subgraph counts may not be so robust to change in models, but things like convex relaxations might be pretty robust to changes in model. So I think, yeah, like I think that's a great, direction for future research, like getting algorithms that are based on things like convex programs that would be robust to change in the planted model. Right now, we can only handle that for really, I quoted this result here, like you really need the noise rate to be quite small to make that work, even in this correlated random graphs case.
Yeah. Thank you. Any more questions?
Yeah, so I was wondering, so on the requirement that the average degree has to be a union of those two intervals, like, do you see that in any other kinds of problems?
Oh, no, I think that even in this problem, that's like a very, I don't think it's inherent. I think it's artificial. It's, like, in fact, I'm, yeah. So I think that you wouldn't, like that shouldn't be there. That's a limitation of our proofs. Yeah, so, and I can't think of any other case where that shows up, but maybe someone in the audience, where it's not an accident of the proof that it shows up.
Oh, and like as for why you have this intuition that it like shouldn't be disjoint.
I sort of think that these like large families of strictly balanced graphs probably ought to exist at every, like there's nothing really special about, like I sort of have the conjecture also that if you sample a random graph from, yeah, I mean, okay, I don't know, I mean, but I think if you sample a random graph from the correct model that wasn't like, start with a deregular random graph and then subdivide all of the paths and stuff, maybe it would be easy to see that so like strict balance is a property that random graphs should have, kind of, and if you sample from the correct distribution, I think you would have it like at every kind of degree regime. Yeah.
Okay, thanks.
Any further questions? Okay, so let me thank the speaker again, and the lecture resumes at 2 p.m. Pacific time. Bye-bye.